Vision models can learn from millions of images without a single human annotation. This isn't theoretical, it's the profound reality of masked autoencoders, or MAE, a self-supervised pre-training paradigm that's reshaping computer vision. We're talking about vision transformers, usually ravenous for labeled data, becoming incredibly efficient with MAE. At its core, MAE takes an image, heavily masks a large portion of it, say 75%, then presents these fragmented visual patches to a standard vision transformer encoder, the model's tasked to predict the missing pixels of those masked patches. Think of it like solving a jigsaw puzzle where most pieces are hidden, but you're only given the edges and asked to fill in the entire picture. The critical insight here is that the reconstruction target is simple pixels, meaning no complex labels or external knowledge are required. The network simply learns strong visual representations by understanding context and spatial relationships within the image itself. It's a remarkably intuitive form of self-supervision. Practically in PyTorch or TensorFlow, this involves an encoder transforming visible patches, and a lightweight decoder, often just a few transformer blocks, that operates only on the masked tokens predicting the original pixel values. During fine-tuning, you simply discard the decoder, using only the powerful pre-trained encoder for downstream tasks. This streamlined process results in encoders that are exceptionally robust, even with relatively small datasets. Consider medical imaging, where high-quality annotations are scarce and costly. An MAE pre-trained vision transformer can learn powerful representations from vast amounts of unlabeled X-rays or MRI scans, then fine-tune on a tiny fraction of labeled images for specific tasks like tumor detection. This significantly outperforms purely supervised methods that would struggle with data scarcity. Or even contrastive learning approaches, which might overfit to superficial similarities in such specific domains. A subtle but critical point: MAE leverages an asymmetric encoder-decoder design. The encoder only processes a small subset of visible patches, ensuring computational efficiency during pre-training. But the decoder, crucial for reconstruction, only sees the masked tokens predicting pixels for what the encoder didn't see. This forces the encoder to learn incredibly rich semantic representations of the unmasked portions, as it must infer the vast missing context. Ultimately, MAE redefines data efficiency for vision transformers. It empowers us to leverage the sheer volume of unlabeled visual data, transforming how we approach foundational model training. We can now build sophisticated vision systems with drastically reduced reliance on expensive human annotations, accelerating breakthroughs in fields from autonomous navigation to scientific discovery.